Hello everyone, this is a demonstration of supervised network intrusion detection classification on the UNSW NB15 dataset. All of my code can be found on my GitHub, which is right here. I will have a link to it in the description. And let's begin. We start off by importing Sklearn and Xgboost, Lite GBM, and perhaps a few other things below. By the way, this right here, it's for whether you want to do binary or multi-class classification. If you do binary classification, you get approximately 96% accuracy, and with multi-class it'll be considerably less, and that's what I just ran prior to starting recording. So we start off by getting the train and test dataset. We combine it for feature engineering and demoing purposes, just to make our life a little easier. We can see that the contamination of our data set is quite high. Since it's above 0.5, technically our contaminated data is actually our non-malicious data, which is just a little quirk of this data set. So continuing on, we encode everything with we run a label encoder on our data set. And we can see that we have a variety of different types of data. Some of it is malicious, while other of it is benign, just labeled as normal. What we could do in theory is to drop the columns which have a low standard deviation or that have a low correlation. Personally, I'm not a very big fan of this unless you find that computational expense is a huge issue, which it is no doubt for this dataset. However, I will mention that getting rid of data with a low standard deviation could be stupid, because suppose you have a feature which has a 1.0% correlation with the target, whether it is malicious or not malicious, and this will relate to the conditional probability, which itself relates to the joint probability distribution. So long story short, suppose you have a variable, it has a 100% correlation with our prediction, but when it is present, it has a 1.0 conditional probability with what we're trying to predict, but most of the time it is just a 0. So that would not have a very high correlation, but that would have a whole lot of quote-unquote information. You just have to think about this a lot just to get an understanding for what this really means. On the side of correlation, imagine you have a neural network could pick up correlations that other methods won't be able to pick up. So personally, I'm not a fan of getting rid of low standard deviation or low correlation features. However, you could consider that. I actually wrote a blog on this, so you can find it on right here. Is exactly what I just mentioned. I actually went much deeply when discussing a different data set. Anyways, I just skipped that here because I actually find that there's no practical benefit to it other than computational cost. Over here, we're going to have our test set size be 20%, and we're going to start off by benchmarking before any type of feature removal. So at multi-class, we actually find that we have an average of about 83% or 84% accuracy. Our best classifier has an 84% accuracy. However, one classifier, particularly Lite GBM, does not do very well. So continuing on, let's try making this into an ensemble, and we can see that our ensemble will actually cover up the screw up of late GBM. So we end up having a 82% accuracy. And if you were to use something like Catboost, which is another gradient boosting classifier, by the way, one of these is from a open source foundation, one of these, perhaps this one, is from Microsoft, and the last one is from Yandex, which is the Russian version of Google. It's a Russian search engine. Pretty large company, it's just not very well known in North America. Kind of like how Huawei used to not be very well known in North America until about 5 years ago. Anyways, we can also try this one thing called recursive factor elimination. If you're wondering what it is, I recommend that you just check out the Sklearn documentation. So after recursive factor elimination, we find that bringing it down to 10 dimensions from our original 42 dimensions, we retain a 82% accuracy on some of our classifiers, which is actually very competitive against using all 42 dimensions, as you can see over here. What this means is this is significantly more computationally efficient. So you can reduce dimensionality with machine learning rather than doing it in a statistical manner, and you find that it works out quite well. Similarly, you can use something like singular value decomposition to bring it down to 10 dimensions. However, SVD is quite literally incompetent in the face of recursive factor elimination, though recursive factor elimination is more computationally expensive. Furthermore, here's a little bit of a benchmark with feature removal with recursive factor elimination only. You find that for binary classification, so matter of fact, sorry about this, just ignore this. This only makes sense if you're running this data with running this on the binary classification. This is irrelevant for multivariable. And that is it. I did a lot of deep learning on this data set. However, I left that for different notebooks. And if you're wondering what this data set actually looks like, this I actually stored in a different variable, but I'll show it to you guys too. T-SNAS on 2 dimensions looks like the following. T-SNAS another dimension. T-SNAS on 3 dimensions looks like this. The classic PCA looks like this, or like in 3 dimensions like this. So I hope this gave you some inspiration on what you can do for supervised intrusion detection on your own data set, and good luck with whatever you're doing.